good. Good? Ready? Okay. Good afternoon, everybody. Thank you for coming. My name's Neil Palmer. I'm the CTO for the FIS Advanced Technology Group. Today, we're here to talk to you about this. It's a very long-winded title, I do realize. We originally we wanted to call it How We're Going to Save Western Civilization, and all I got was this corporate branded t-shirt, but that wouldn't fly with marketing, so you got that. What we are going to talk to you about today is how we are planning to ingest every piece of stock market data from the US markets, process them in 4 hours on a daily basis, that's 15 terabytes, and make it available for market reconstruction and analysis to the regulators. And so to help me with that today, and we'll demo a little bit of what we've been building, I have Mr. Carter Page from Google, lead for Bigtable, and Mr. Todd Ricker, principal engineer from FIS, who's going to be driving the demo. A little bit about us. FIS is the largest financial technology firm in the world. We build everything from online banking systems to ATM software to help you get your cash out, for those of you still use that, through to asset management software, trading systems, risk, everything at the back end of Wall Street. My world's a little bit different. My world is to go out and do work in other industry verticals, to look at media, to look at internet, and to figure out what's going on in emerging technologies in those industries. We find that those industries are typically about 18 months ahead of the financial services firms, and so doing real work there allows us to bring that knowledge in-house and apply it to our products and to our clients. So the problem we're looking at today is, what on earth is going on in Wall Street? As you may have noticed in the media over the last couple of years, there's been some issues with the well-functioning of Wall Street. And you look at the film, The Big Short, you look at the book, Flash Boys, there's some serious issues going on in terms of the systems and how they're being managed. And I think part of that is because a lot of people have forgotten that up until about 15 years ago, Wall Street drove significant technology innovation. The acceleration, the electronification of the markets, the straight-through processing piece was all a competitive advantage to them and made them a lot of money. The problem with that is it's left us with a large number of very disparate systems on very disparate technologies across ever-increasing numbers of broker-dealers and execution environments. And so when you couple what is essentially technical debt with what could be viewed as regulatory debt, you have a much greater risk profile to the well-ordered functioning of the market. And given the way our economy and our way of life is based on the well-ordered functioning of those markets, this is not a good thing. And so there is a need for much better forensics in terms of how the market's behaving, and so that when things do go wrong, we can actually figure out what has happened. So I want to touch a little bit about where we've come from, and before we get to what we're going to talk about, which is the consolidated audit trail. It was only about 40 years ago we still had pit trading, paper trading, like you see in all the old movies. And over the space of 40 years, we've gone from that through to the high-frequency trading that you hear so much about these days, where essentially 75% of the trades placed are algorithmically driven. This has greatly increased data volumes, and it's greatly increased data complexity. And so it's gotten to the point where many of the Wall Street firms have embraced this electronification quite aggressively. It's not necessarily a bad thing in of itself. It's driven a lot greater price efficiencies. It's actually done a better job for a lot of even retail participants there. But when things do go wrong, they create anomalies in the market, which creates unfairness. And people suffer as a result of the consequence. And so the goal is that we need to have a single system these days that allows people to understand what happened. And so you can see here, in the last, not even 15, 20 years, there's been astronomical data growth in the financial market. It's interesting because even though there's been astronomical growth, it's not uniform growth. It's not one-way traffic, if you will. You can look at the spike on this graph and see 2008 volumes reached peak, and then they plunged as a result of the recession and the bubble that popped then. Also, what happened was that in 2010, there was what's known as the flash crash. And this was a problem with the markets and the trading where several $1 trillion was wiped off the US markets in the matter of minutes, and then mysteriously reappeared about 30 minutes later. Now, I don't know about you, but having several $1 trillion magically disappear and then reappear is probably not really a good thing for life in general. And so the SEC, as a result, put together a proposal to create the Consolidated Audit Trail, or CAT as it's known. We have our own very special designed CAT symbol, not just your usual grumpy cat stuff. Thank you very much. And so really the goal of CAT is to track every life cycle event, every tick, every trade, every piece of data that's involved in the US market in one place. Previously, the quote has been that regulators have been trying to use bikes to catch Ferraris. And so our goal is to build the next generation system that will allow them to understand in a reasonable amount of time what is happening in the market. And so this is a lot of data, right? This is taking data from all these silos across all these banks, these broker-dealers, the executions, the dart pools, and bringing them into a single system. We're going to have to ingest 100 billion market events per day. We have to process them in 4 hours. That's 15 terabytes a day for 6 years. That's 30 petabytes of data that, and here's the kicker, we have to be able to query the whole 30 petabytes. We are one of 3 final bidders for this process. The process started 4 years ago with over 30 firms involved. It's down to the final 3. With the help of Google, we're going to show you a little bit about what we've built and managed to achieve so far. There's 3 core problems we'll go through. Just the sheer scale of ingesting that much data, the sheer scale of processing that much data in what is, frankly, a ridiculous time frame, the 4 hours. And then the final problem is how do we actually get any actionable information out of all that data, right? There is absolutely 0 point in us throwing this into a big black hole and we can't do anything with it. Although, when the original RFP came out, it was about 250 pages long, and there was 2 lines in it about querying. It says, we need batch and we need ad hoc. So we were like, well, thank you, that's extremely helpful. So what we're going to do now is we're going to walk you through, we're going to kick off a demo that's going to come in several parts around in data ingestion, processing. We'll talk about the linkage, because we have to be able to link lifecycle events across multiple reporters. And then we'll show you some of the visualization tools we're creating to be able to actually interrogate the information. And so for that, I'm going to hand it over to Todd to kick off the demo.
Thank you, Neil. Can we get my demo screen up here?
All right.
Perfect, thank you. So I'm going to just start by kicking off the job, and then I'll tell you what it's doing. You can see I'm about to run a Maven command. I'll say I'm doing a 2-part demo here. I'm running the data processing piece first, which is a Dataflow job. And then a little later, we'll look at the data and we'll see how we can visualize that data. So let's kick it off. Should be exciting. It's executing a Dataflow job, that Java code sitting on my local laptop. It's pushing it out into the cloud right now. It's just standard, Maven stuff going on. So what does the job do? The job is going to process 25 million synthetic trade events that I generated this morning from real price data from this morning. So at the end of the demo, you can compare our prices to the real prices. You'll see they're the same, but it is synthetic data. So the job kicked off. I'll tab over to the Google Cloud Console. We should see it running. Very good. So what the job's going to do, take those 25 million synthetic trade events. They're stored in Google Cloud Storage. They're FIS messages. FIS is the standard protocol by which exchanges and banks communicate trade events. So it's going to copy those out of Google Cloud Storage. It's going to insert them into Bigtable. And then we'll make another run through that data and create the links between the trade events. So where they have relationships, we'll link them at that phase. That's the part that's difficult at scale. And then finally, we'll copy all that data from Bigtable into BigQuery so that we can easily visualize it and query it. So Neil, why don't you tell us more about linkage?
Okay. So we're going to let that keep ticking along. Fingers crossed I haven't angered the demo gods of any time soon. So what a lot of people maybe don't know is that when you order stock, when you purchase a stock online through your broker-dealer, be it Fidelity, Charles Schwab, your cousin Vinny, whoever, right? If you've just cashed out in some highly successful IPO and you need to reinvest it into something a bit more interesting, and you want to buy 10,000 shares of Google, for example, you click submit, you get an order confirmation number back straight away, but that is not how that trade gets executed. That trade gets routed to your broker-dealer, and your broker-dealer is governed by a couple of regulatory things, one of which is best execution. They have to make sure that you get the best price for that trade. But after that, they have a lot of options about how they might want to fill the trades. They might route it to multiple exchanges. They might route it to other broker-dealers. They might fill it themselves. They might send it to dark pools. A huge range, wide range of areas they can do that generate multiple hops in the trade. And in fact, most trades these days that are actually executed at the point of execution on Wall Street are typically no more than 200 shares because they don't want to move the market. They don't want to tip their hand around who's buying what. And in fact, there was an incident earlier this week where somebody fat-fingered some Apple shares, and you could see a huge spike over several seconds in Apple share prices because somebody was trying to buy 70,000 shares instead of 70. So what this does is it generates thousands and thousands of life cycle events, billions. And we have to reconstruct them. We have to be able to connect the order execution back to the ultimate beneficiary owner, the person who ultimately placed the trade. Now, the problem is, this is a regulatory transactional system, right? This is not log file analysis. We cannot drop one of these events. We cannot make a mistake. And so we're not allowed to use pattern matching. We're not allowed to use fuzzy logic. We have to take the trade events and connect them from point of execution, point of fill, all the way, reconstruct the tree, all the way back up to the original order. And that's complex. It takes a huge amount of processing power, and we have to have very flexible schemas in order to be able to handle attributes that may vary based on reporter, may vary based on asset class, may vary based on time. And so for that, we chose Cloud Bigtable. And to talk about Cloud Bigtable, here's Carter.
Thanks, Neil.
Yep.
Hi, everybody. My name is Carter Page. I'm the engineering manager for Cloud Bigtable. I'm also the engineering manager for Bigtable internally at Google as well. At Google, we've had our fair share of big data problems. With an audacious mission to organize the world's information and make it universally accessible and useful, we've had to come up with a whole suite of big data tools, as you've heard all for the last couple of days. We developed these different tools, GFS, MapReduce, Bigtable, Dremel, and all these things start to come together into our cloud tools to allow Neil and the team to build something like this. And all these things came out of real needs that we had. They were actual problems we had at Google, and we sat down and figured out what do we need to engineer to solve this problem. So for instance, very early on, we're basically collecting a copy of the entire World Wide Web, and we're trying to figure out where do we store this thing. And you can either have an application trying to figure out how to shard it across a bunch of different machines, which puts a lot of burden on the product team, or you can come up with an abstraction, an API, which simplifies this actually very complicated process underneath. And we did that and became GFS. GFS was later upgraded, essentially replaced with Colossus in 2010. It also has a key value API in front of it that we know internally as Blob Store, and externally you would know it as Google Cloud Storage. As we were building out these files, we have a place to store them now, but now we're getting a lot of updates. And while a file system is great at doing blocks, it's really bad at doing small reads and writes. So you've got a copy of the web, and you're updating the latest pages that came in. If you have just a file system like we had before, we had to rebuild the entire index from scratch. And this was taking days, turned into weeks, and was approaching a month, and was creating a problem. You had data staleness issues, in addition to the fact that this was costing more and more resources and time to actually run. So we had to build a database on petabyte scale, and what we came up with was Bigtable. We launched an internal service in 2006. So this was actually our internal cloud. Externally, we launched this as Google Cloud Bigtable a year ago, but this is actually abstracting the internal cloud service we've been running for a decade. So you have a whole bunch of data, and you want to be able to do an ad hoc query on, say, 1 trillion rows, and you want to be able to, just ask some basic questions of it. It's not a very easy thing to do without something like what we developed internally, Dremel, or if you saw the previous presentation, BigQuery, which is also talked about a lot here, and there's a fun kiosk on BigQuery out there. And then you've got all this data, you want to do something with it, right? You want to identify which photos have cats in them. You want to figure out what your page ranking is going to be for your search index. You want to do something useful with it. So you need to actually have data processing at scale, massively parallel processing. We built 3 tools internally, MapReduce, Flume, and Millwheel. And these things became what you see up here, which is Dataflow. And Dataflow is the kind of conductor that helps tie all these things together. And it works, it's a really key piece to be able to do big data analytics. You need something that can actually talk to Bigtable, for instance, at the scale that Bigtable becomes useful. So imagine what you can build if you have these products, these services internally that just will magically scale for you, whether you have 10,000 customers or whether you have 100 million customers. You can think about the product and not think about how you're going to scale it up at each step along the way and how you're going to deal with sharding your databases. When you don't have to think about it, you can focus on building really great products. And I really think that we can attribute a lot of the product diversity that Google has been able to develop over the years to this really rich infrastructure. And this is the same infrastructure that is in Google Cloud Platform. And that's, I think, what makes this really exciting for a lot of us, is the idea of this was an enabling factor for Google to be able to grow and have this diversity and richness of our products. We think that external customers will be able to find new and exciting ways to be able to do things when they don't have to worry about the basics. So back to Cloud Bigtable, which is, again, my area of expertise. So I'll spend a couple of minutes on this. It's the exact same service on Cloud Bigtable as photos and maps and calendar and et cetera talk to. It's not an abstraction or a Bigtable Lite version we have running. It's actually the exact same service. It just has a external cloud API kind of attached to it. Cloud Bigtable, for those of you who don't know, I'll give you a quick introduction. It's a NoSQL database, so it's not relational. You define columns as you insert them. It supports sequential scans, which basically lets you do some clever things which are good for time series and the like. And it'll auto-adjust access patterns. So you've got this large sharded database, and as you change your access patterns, it will adjust the data for you, so you don't have to think about it. Briefly, how it works is you have a set of clients out there, usually a lot more than that are talking to a set of nodes. And the nodes are basically just CPU and RAM. And they will pin to a certain chunk of the actual data that sits in the Colossus file system, which handles our durability and basically replicates that data for us. And each node will serve out a chunk of that data to the clients. What this allows us to do is in Cloud Bigtable, allows you to scale processing and file size orthogonally. So for instance, if you have a lot of data, but you're just kind of trickling it in over the course of a few years, you can have a few nodes and let that grow. Or if you're doing a lot of really fast processing on a couple of terabytes, you don't need to actually scale your nodes to the same size as your actual data. So I was talking about it learning access patterns. For instance, imagine you have a hypothetical situation where you've got a really small, 3 nodes is a very small cluster, it's for production. but it's like the minimum size we allow in Cloud Bigtable. But imagine, for illustration purposes, we have a 3-node cluster, and by the luck of the draw, all your clients are asking for the data that's sitting in the node on the far left. What Bigtable will do is it will identify these load patterns as they start to appear, and it will immediately start shuffling data around. It's actually really fast at doing this. It can move entire chunks of data in a couple of seconds. And if the access patterns change again, and there's a new server that starts to heat up, it will also start to rebalance. And that's useful when you start to figure out, when you start to think about how you want to scale it. You don't have to, well, basically what you get out of this is you get linear scalability. You can go from 3 nodes to 30 nodes, and you get a 10x increase in terms of your throughput. You can go from 30 nodes to 300 nodes, you get another 10x. It is linear all the way out. You go to the kind of sizes that they'll need to run, it just keeps going. And that's actually really great for planning because a lot of times these distributed architectures will eventually start to flatten out a little bit on the curve. But you can actually count on your line going straight, and you don't have to do a load test at an order of 1,000 nodes. You can do it at 100 nodes and know what resources you're going to need for that higher set. It also gives you confidence, as you grow, you don't have to worry about it too much. Your cost of your underlying database can be just a function of your growth. So internally, getting to the point where we exposed Cloud Bigtable last year, it's a lot of engineering that we did internally to be able to have this cloud product. Again, it's essentially a cloud product internally. We had to teach Bigtable how to configure itself. It started with thousands of different flags and configurations that were really confusing to internal engineers. And we realized that Bigtable could actually do a better job figuring out how to configure itself correctly than our engineers could a lot of the time. And this results in a simpler control plane on the cloud interface for it. We do a lot of isolation. We had to make sure that one product at Google that was having a very big day was not interfering with another product at Google. And as I showed before, there's a rebalancing aspect to it that we've been spending a lot of time on. And this is true with all these products you're seeing up here. These aren't things that were invented for cloud. These are things that we've been developing and running and using internally and are instrumental to operations for the past decade. And the same sort of work we've had to do to be able to make all these products, so these Google products, coexist side by side, that's actually what puts us in a great position to have products that work very well in the cloud scenario. So with that, I'll hand it back to Neil.
Cool. Thank you very much. So what Carter's just been describing was very important for us from a design decision perspective, right? The levels of load we're talking about, but with Google taking the technologies that we already know scale at that level, if not beyond that level, for me, that was a weight off my mind. Like, I don't have to worry about this. Is this going to scale? I know it's going to scale. So I'm going to talk a little bit about the high-level architecture, but first, I'm going to check in on the demo. Todd, how's it going?
It's going pretty well. We've ingested 26 million order events, market events. We've linked them, and we're finalizing with the BigQuery copy. It'll be a race. We'll see what happens.
I'll slow down.
Yeah.
So just a little bit about the thought process when this started in 2012, and a lot's changed in those 4 years. FIS runs a lot of infrastructure and a lot of processes and a lot of applications for financial services firms. But we looked at the scale of this and we thought, no, too big. We can't handle that. We started to look at private cloud as an option. Addresses some of the scale issues, definite economic issues. And so we came to the point where we're looking at public cloud, and it became clear to us, that they had the scale, and you could already see the impact of the economics and the impacts of Moore's law with prices decreasing. And so we decided that was the way to go. I have to say, at the time in financial services, that was not a particularly popular decision. When we first walked in front of the regulators with Google in the room and told them what we were planning on doing, they basically were like, you are out of your mind. And so on one hand, the process has taken a really long time because that's the way regulatory systems work. On the other hand, that's good because we've had the journey that's brought the regulators along with us in terms of understanding what public cloud is, how the security works, and especially the economics, right? And the continued price reductions in all the public cloud providers has made a significant difference in terms of the risk-cost-benefit equation. So in terms of high-level architecture, you've heard Todd talk about some of it. We have a direct peering connection with Google in NY5 in the data center there. It's a 10 gig pipe. Right now, we're pushing L2 equities data in through it on a regular basis. We're only consuming about 500 megs of that bandwidth. We've got 20 times headroom ready to go. It smokes. It's basically fixed drop copy the files into cloud storage. We use Dataflow to transform and do an initial validation on the data and insert it into Bigtable. We run another job that then does the linkage on all the events in Bigtable before extracting it out to BigQuery. Bigtable was critical because, as I said before, we have to link from the ground up. And so when we get an event, unless it's an absolutely new order, unless it's the very first step, what we know is we have the event and we know its parent event. And so what we do with Bigtable is essentially we write a put, we do a put and put the row in, but we also do essentially another put which puts a phantom row in for the parent. And so it allows us to know, by constructing the column names on the fly, whether or not the previous or subsequent steps in the chain have already been found. Part of the problem is we have no guarantees on when we're going to see this data, right? The banks have to report it by, I believe it's 8 p.m. end of day trading. We have 4 hours to process it, but we don't know the orders. We don't know the sequence of the orders of when they come in, none of that. And so you have to be able to very flexibly see whether or not the full life cycle has been found. And there are some orders that you won't. Some orders are out until cancel. The other big thing that was important to us was BigQuery and the API access to BigQuery. I don't know about you guys, but I hate getting reports from requests from business people to write me a new report. That drives me crackers. So, and because we have to bring an entire industry with us, right? We have to move an entire industry from a variety of different regulatory systems onto this one, and it's an industry that is basically saying, you're going to pry Excel from my cold, dead hands, right? So the fact that BigQuery means we can plug Excel into it, we can plug other BI tools into it without our involvement was very, very important. And so we'll talk a little bit about that later on in some of the visualizations that are going on. And we haven't gotten this far yet, but I think the next major challenge for us is going to be around testing tools and regression testing and things that we give the industry so that they can understand how our software is working, how our system is working, how their order management systems are operating. When they upgrade their software, how do they know that it's compatible with what we've done lately? And I think that's going to be a big, big challenge. So I think, are we ready? Are we going to look at the demo?
Yes, yes.
All right.
The demo gods have smiled on me and the job completed. So first I'm going to show you a BI tool on another set of data. This is not the data we just processed. This is a BI tool called ClickSense. It's a web-based tool. It uses the BigQuery connector, so we can nicely connect it to our data sources. It's, as BI tools go, you can set up the visualizations without necessarily using a programmer. So, your business users can set up their own visualizations, help them do their own jobs well. And this is powerful stuff in an industry that's, still primarily run on Excel spreadsheets. So here we're looking at the most active underlying options from today, from this morning, 9 market open till about 11. We have a pie chart, we have a bar chart, pretty simple stuff. You can see that the Spiders ETF was the most actively traded option this morning. That's typical. Spiders is a ETF fund that's tracking the S&P 500. So on most normal days, it's going to be a very high volume. Little odometer, great. Very simple, but powerful stuff. So let's move on and look at another visualization that adds some fun. So we have here a heat map. It's the same data source, same underlying data. We've added the dimension of the trading venues up at the top there, so you can see the various exchanges. The darker color denotes higher volume, so we can easily look across all the exchanges and see that spiders on the ISE exchange was the highest volume this morning. So that's fine and good. Let's look at something even more complex. This psychedelic looking thing is the zoomable sunburst visualization. I think that's pretty arbitrarily named, but we can really drill down and see even more data with this visualization. The inside wheel here is the various highly traded options, underlying options. So we see spiders here. We can drill in on that, and then we see that middle wheel is the various exchanges. So we can see that on the ISE, spiders had the highest volume there, and then we can drill in even further and see that the majority of the orders were puts. So that's great. It's a BI tool. It doesn't necessarily require programmers. The next thing we built was a custom app, and this is going to visualize the data we just processed. So my web app is connected up to that data that we just processed, and it is built with D3 and also uses the BigQuery data connector. So let's look at Google stock for this morning. And there we go. So we have a scatter plot here. These are all market events. This is my synthetic market events, but based on real pricing data from this morning, from market open until about 11. The various colors are different market event types. So these blue are new order events. There's routing events and a bunch of different kind of events. But let's look at one of the filled events, because they're the interesting ones. They've reached the end of their life cycle, or at least a portion of them has. Okay, so here is our D3 visualization of linkage, right? Neil walked us through what linkage meant. This is a single order and the life cycle it took on to be filled. So if we see the blue dot up there, that was the new order. When I mouse over at the top, you can see the specifics of the order. So 458 shares. It was routed through a couple different broker-dealers. And then at this point, the order was split into, what, six smaller orders. So they branch out. We can see that what started as a few hundred shares is now 91. So we're breaking down the order into smaller bits. Got routed again, and then finally it was filled. And the other path is it goes out, gets split a bunch of times, and it's not yet filled. So those are still, those smaller orders are still open. So again, this is a D3 visualization using the BigQuery connector. It's all client side. It's deployed to App Engine, but there's really no smarts on the app server side. It's all client side. So the final thing I'm going to show you is the real Swiss Army knife of data processing. This is Google Cloud Data Lab. It's a Python-based tool. It's web-based. It's built on IPython notebooks. I've hidden some of the code here, the rendering code, but it's not too much. I'm calling it there at the top. You can see the BigQuery query that we're issuing there. It's pretty simple. And then what this graph is doing, the underlying data is the price data for Bank of America on a day a couple months ago back in November. So it's 1 day of price data for Bank of America. The yellow line is the moving average. You probably can barely see the yellow line, but there's a moving average line there. And the red dots indicate when the price has gotten 3.5 standard deviations away from the moving average. So these are like anomalies in the price during the day. So this is interesting to traders and auditors and a bunch of people. So this is your data scientist tool, people who can program, people who know Python. You're able to use NumPy, SciPy, Pandas, a lot of the real powerful analytics tools that we have available. So that's 3 ways of looking at our data. Back to Neil.
Thank you. So you kind of get a feel there, tools for business users, tools for day-to-day operations, and then tools for your data science guys to do the exploration. Just a couple of lessons learned from going through this process. We originally used MapR when we first built it. Native Hadoop migrated to Dataflow. We love Dataflow. The abstraction level is fantastic. Cannot recommend highly enough optimizing your code. One stray logging statement at this sort of scale equals about a 5-hour delay. When you're developing your pipelines, we found it helpful to generate multiple data sets, static data sets that we could then rerun both different configurations and different logic at the same time. Sometimes the configurations that you need vary based on your data load, data scale. So don't assume that a small number of large workers is better than a large number of small workers or vice versa. It is very contingent. You will spend quite a bit of time playing around with those to figure out what actually suits your job. And then really learn to tune the job to maximize the worker throughput. That we found was very important. Where are we going in the future? So the cat bidder is supposed to be chosen this year. Whoever wins then has 1 year to get all the major exchanges on board, which is just a silly short time frame. Year 2, the major broker-dealers have to come on, and year 3, everybody else. So 3 years to build and deploy to the entire industry. After that, things could get interesting, right? Different asset classes, different types of transactions could be brought in. Again, bigger, wider, more holistic view of what's going on in the market. Potentially move closer to real time. Real time for the SEC, for the market, at the moment is about 5 days. That's what they consider real time. Dataflow supports streaming out of the box. We can potentially contract this whole process as much as the people on the other end are able to handle that. And then we're having discussions about opening up this. Right now, this is a regulatory system. We think it's quite important that the broker-dealers be given access to the data as well. Right? We want the broker-dealers and the regulators to be having conversations and looking at exactly the same data. The goal is to build a better regulatory system for our stock markets. And if you do that, then the broker-dealers can potentially shut off all sorts of internal systems that they are now running because they have to, right? And you become to sort of a global source of truth that's going to save everybody money, time, and effort. And if you take that concept a little bit further, I don't do it with them very often because it scares the living bejesus out of them. But if the data's anonymous and if the data's secure, well, what if you opened up APIs onto that data and let the market innovate around it? And so for us, it's exciting because no matter who wins in this point, all post-trade data will be in the public cloud. Right, so think about that. All the arguments that have happened about it's not secure this, it's not secure that, done. The regulators would have put all the data in the cloud. And so hopefully that will bring and spur the same type of innovation that we've seen in media and internet to financial services and eventually to other regulated industries such as healthcare, energy, et cetera. So, conclusion. Scalability and security, right? Scalability, no-brainer. Using those technologies, we can already go higher. Security, again, that was a great conversation over years. Google never had a breach, lots of breaches at the banks. I mean, the kind of conversation solved itself there. Economic cost, again, decreased pricing, knocked a huge amount of cost off the bid. Very valuable to everybody. And the elasticity, because of the trading daily volumes, is another key point. So the goal is to change not just the where, but the how of financial services computing and what can be done. This has never been done before. It's only recently it's been technically viable. It's even more recently that it's been economically viable. So we're pretty excited about it. However, one more thing, which I think is the phrase that gets used in this part of the world. We ran a test with Carter's team 2 weeks ago. We processed 25 billion market events in an hour, end to end. Well, technically it was 50 minutes, but I didn't want to be seen as showing off. So That is 20% more than the highest market volume day ever in the US markets. We created 25 billion fixed messages and ran exactly that demo in 50 minutes. We used 3,500 Bigtable nodes and 300 standard 32 VMs to do that, which isn't that many when you consider those numbers. Sustained 22 million events read a second, 16 million events written a second. Sustained. Burst, this is where it gets silly. It starts to get silly at this point. 34 million events read a second, 22 million events written a second. 22.
So I just want to jump in here and provide a little context. We see a lot of traditionally large numbers at Google, and not to be cocky, but we often kind of yawn at terabytes and things like that. These are actually really big numbers, and kind of made our team blush being able to pull them off. To put it in context, imagine 34 million events per second is the equivalent of over 2 billion events processed every minute. 22 million writes per second is over 1 billion events every minute. And usually when you talk about processing, billions of events, you generally are talking about, and this is in big data context, we did a billion events. Usually saying I did 1 billion events, in a day, or I did it over, hours. You're never, now we're saying that we can do billions in just a single minute. These are the actual reads and writes to the database itself. So this is to a persistent storage system, which actually, even though the reads number is bigger, from an engineering standpoint, the writes is actually what we're prouder of, and there's actually a lot more work that goes into that. Because each of those writes are durable. They're not cached. So to put it in another context, if we were in the middle of this process that's going, the test we did over 50 minutes, and we're writing at a rate of 22 million writes per second, and we simultaneously yanked the plug on all the machines, every single one of those acknowledged writes has been preserved and will be there when it comes back. And that's something we're actually really proud of. And I think it's a pretty extraordinary, large thing.
Right. So we're going to translate that into just sheer gigs per second, just because. So sustained 22 gigs reads per second, 13 gigs written per second. Burst 34 gigs read, 18 gigs written per second. It was just smoking. And so it was an utter pleasure. We've had more fun than we know what to do with. And we're really looking forward to taking the system forward and seeing where we go with it. And also talking about where else we can apply this type of technology. So I think that's it. We'll be around for questions if you need us. Thank you very much. All right.